Okay, so next is collidable. So within collidable, the major changes that were done was now the user could choose between multiple different collision volumes, such as B-sphere, ABB, or OBB, and then there's always a constant internal B-sphere for collision tier checking for collision tests. So here are the enum classes for choosing. On here's null pointer. There's a pointer for a B-sphere and there's a pointer for a collision volume. Here's a destructor that destroys it all properly, and then in actually setting the collider, it grabs the model, but then passes in a volume type, which is the enum class, and it creates or it sets the collision volume to that based off of whatever's passed in for more user-friendly usability. And it owns 0 graphic objects. But past that, we could go into the different volume types. So from before, instead of just a generic class, we now have B-sphere. B-sphere itself doesn't really need that much. It pretty much just needs the model and the world matrix that you pass into it. Going more into depth, it does not hold a graphic object to show itself. That's all handled by visualizer and such. But it also uses the double dispatch visitor pattern. So here's the intersect accepts. Very simple, mainly because that's all rerouted into the math tools itself. And then the new visualizer for the beat sphere itself is within the draw debug view call code. And then next we can go into OBB. OBB is slightly similar. It just has a few more getter functions to help out, not really help out, but to go further into the math for intersection on such a complicated type within the math tools, which I'll show in a second. ABB is slightly more, not easier, but less complex than the OBB version, only because it's not changing its rotation within local space and such. Only difference is there are a few functions within here, as well as a few variables within here that are very similar to OBB, such that the OBB and ABB test are almost identical, just taking in different collision volume types, which I will show in 1 minute. I guess to go into depth, what really occurs is to modify the collision volume ABB. We're grabbing local min and max corners, grabbing the half diagonal, grabbing the world center, setting the world, and setting a scale factor so that the initial math tools could sort out all of that when it's needed to actually call. The data update itself is for ABB goes through the whole list of verts and finds the max and min corners. For OBB, it's slightly different. If I could get to it in time, there we go. It's different in that it's a lot simpler and it's just grabbing the max ABB and OBB, not ABB, but the ABB of the actual model and applying it as such. Collision volume ABB also has additional compute data, is one to run off of B-sphere so that it can grab its ABB based off the max and min, I guess, vector points based off the radius within B-sphere, and then calling forth its whole shenanigans for calculating the maximum axes. And then there's one for computing data based off of a cell, which only passes in a max and min corner. And then the rest is all just intersect accept stuff as well as here. We could then go into the intersect accept itself and within PW Math Tools. So looking at Math Tools itself, I remember from the very first time, or Engine 1, you were complaining, not really complaining, but you made a fair point that Math Tools should handle pretty much any math functions in general. So all the old math for intersection with like B-sphere and stuff was converted back into what you see now in math tools. Some new math tools, so to speak, that were being used is calculating the axis min and max, doing an axis check, grabbing projection max is overlapped specifically within that. I want to say collision volume, projection max ABB is overlap ABB. Very similar, only difference is between this and the OBB one is just a change in collision volume. Then there's clamping and axis clamping, and then computing the min and max vect that I use specifically. So pretty much any of the intersects are more or less. Oh, no. Pardon me. So here's that initial switch to the new proper intersect. That's not calling it twice. It's a long boy that essentially does a calculation in a one-liner. Here's the intersect for ABB versus collision volume, and then it starts the whole double dispatch visitor pattern. Here's the actual intersect between two OBBs, where it does the 15 SATs. SATs themselves are there. And then those all get fitted into an axis list array, which is then run over for the is overlap function. Only difference between OBB and ABB is that it grabs the actual ABB matrices and such, and then it calls a different overlap. Here's the projection max math. Here's the overlap for OBB, projection math for ABB, and is overlap for ABB. Here's my intersect between OBB and B-sphere, and then the ABBs is basically checking each and every corners, essentially, if they're touching. Not touching, but, you know what I mean? Oof. Well, originally it was this very long boy, but now it's just a triple nested if check. Basically, if any of the corners fail the check, then it returns false, but if they all pass, it returns true. Here's the axis check. Basically, I want to say what is it called? Well, it's called the axis check, but it's like that, the whole alligator boys. Anyway, past that, here's the intersect for ABB and B-sphere, clamping, specifically clamping a vector. Here's axis clamp. Here's intersect between two collidables. So the generic type to start the whole intersect except pattern. Here's the calculate axis maximum, calculate axis minimum, compute minimum vector, compute maximum vector. Alright, from there we could go straight into the collidable group just to show that it contains a collision volume ABB, and that upon where'd it go? Basically, it has a compute math function that's constantly called. Its compute math is called to update the collider, the collision ABB collider. Oof, that was a mouthful. And yeah, that is essentially that. Just to show that in action, I guess I could play real quick. Next on the list is going to look inside the collidable manager itself. But as you can see in the air, there's a very large collider box, and that essentially is an ABB containing all of the, I believe, rockets right now that are being fired off, as well as that group ABB of the spaceships that follow me. So as you can see, I could extend and decrease the size of my bullet ABB based on how many I shoot and which directions. That's that. And now we'll go straight into the collision manager. Oh, hold on. Oh no. Alrighty, so slight bug there. Don't mind that. It was literally me just trying to delete the same object twice. I literally just patched it up by taking that second delete out. Past that, we are going to go in the collision manager real quick. Sorry about the delay. Where the hell did it go? There it goes, system managers. And essentially what occurs within my collision manager is these tests are added based off of, well, there's new tests in general. So there's the terrain collision, and then there's the compute command, question mark? Oh yeah, this regular compute command, which is completely fine. That is specifically meant for the collidable groups. And essentially what happens is within the process collection, these are all ran and executed except for the delete. But in a collision manager's destruction, it clears out everything, but when it hits the delete command collection, it executes it, which deletes that specific collidable group based off of creating said templatized command from that certain instance of the group, and then it finally deletes itself afterwards, and then it clears out everything. Let's see. Let me show you the tiered collision test specifically. So here is the tiered collision test. Start on this side so you can actually see it. So within it, essentially what occurs is you grab the two instances of the groups. Here is calling for showing the visualizers, and this is it calling to begin on the first one, where it checks its own B-sphere against the ABB of that group, and if that passes, it goes on the second one, in which it checks both B-spheres, calling the intersect visit pattern, and if that passes, then it does the standard intersect check based off their actual collision volumes from this intersect here, and that test result shows the specific volumes. Now, within test itself, there's been a lot of changes here. Very similar, except what happens is it checks for the B-spheres twice, and then from there, if that B-sphere passes, it goes into the actual test intersect of the two collider boxes. But to note, it starts at the first bit of the collection and then one after the collection. Most importantly, we could go into the collision test command. Collision test terrain command. So, I guess to go more in depth, I'll go actually in the terrain function itself. Well, actually, no, I'll just give you a quick rundown of what happens. So, it grabs the iterator, or creates candidate cells out of the iterator, or not of the iterator, but based off the collision volume. By collision volume, I specifically mean the ABB created from the OBBs. And then from there, it iterates through that selection of cells very specifically. And per iteration, it computes the cell data with the min and max points of said cell, and then calls the cell intersect between the cell ABB and the B-sphere of that specific collider. And then from there, it'll visualize the ABB touching, and the actual intersect between the two is the cell ABB and the collision volume, which occurs here. And if that passes, it says that it collides with the collision with the terrain is true. I guess I could show you that in a second, or show you where it's being called. And yeah, that's it for this one. I'm out of time.